Hello. Hello. Yes. So thank you. Welcome my friends. So today we are going to talk about a marathon class in fluid mechanics. Okay. So today we are going to complete first chapter is called properties of the fluid. आज हम properties of the fluid के बारे में पूरा in detail discuss करेंगे. So पहले हम क्या करते हैं? We should understand what do you mean by classification of the fluid mechanics. Okay. फ्लूइड मैकेनिक्स को हम कैसे क्लासिफाई किए हैं? सो फ्लूइड मैकेनिक्स को हम तीन कैटेगरी में क्लासिफाई किए हैं. फर्स्ट वन इज कॉल्ड एज फ्लूइड स्टैटिक्स, मींस द फ्लूइड इज एब्सोल्युटली इन रेस्ट कंडीशन. सेकंड कैटेगरी इज कॉल्ड एज दिस इज फ्लूइड काइनेमेटिक्स. In fluid kinematics we are discussing about the effects of forces, and third one is called fluid dynamics. In fluid dynamics we are talking about the forces which are actually responsible for the motion of the fluid particles. Okay, so broadly we have categorized the fluid mechanics into three category. In any one of the book you take, you can find out this chapter separately. First one is called fluid static. The fluid is at rest condition. The fluid is kinematic. Fluid is motion but without force. Last one is called fluid dynamics. Fluid is motion but with considering the forces. So that is the thing. So fluid mechanics classified statics, kinematics and dynamics. First of all, you should understand what the definition of the fluid. So fluid is what? Fluid is a substance which can able to flow. Which can able to flow means what? We cannot say the solid is flowing. Yes, we can say solid is deforming. When you give external force to the solid will deform. But is that fluid will deform? No, it will flow. How it is flowing? It is continuously, it is flowing. What is the forces? We are applying some forces. Okay, shear forces, because only when the shear force, physical kind of force we apply, shear force or tensile force we apply, then the fluid will flow in layer manner. Okay, so fluid is a substance which can flow under the influence of very small magnitude of shear stress, that is called as fluid. So fluid is categorized in liquid and gases. So as far as fluid mechanics is concerned, we are more dealing with the liquid rather than gases. So some basic terms we have to understand. So fluid is a substance which is capable of flowing under the action of the shear stress. So it is saying under the action of the shear force. Okay, so we are applying a shear force. How we are applying later on we will see. We are applying a shear force, then the fluid is flowing layer by manner. So as the fluid is flowing, there is a relative velocity is existing in between the layer. So as the relative velocity will exist, so there is a resistance to offer will created by layers. Okay, so that resistance will be generated. Okay, that resistance will be generated or will be created, and that resistance is called a shear resistance. So however, means what? Fluid is substance which can flow under the magnitude very small shear stress, that is called fluid. Okay, so this is, suppose this is a bed. So this one is the called stationary part and this one is called bed. Okay, and this one is some fluid. Suppose I am taking this one is water, and we are placing a plate on this top surface of the water, and we are pulling the plate. We are actually, rather I can say, we are applying a shear force to this plate. So as we are applying a shear force to the plate, that will happen, it is creating a shear stress on the top surface of the water. Okay, so that shear stress is going to be transport or going to be shared throughout the depth of the water. So what is, as we are applying a shear force to the top plate, the top surface of the liquid is try to move, but what will happen, the next bottom layer, next bottom part of this layer of the liquid, it will try to retard the motion. Why? Because of the viscosity, because water has some viscosity. Okay, intermolecular attraction force, so it will try to drag the motion of the top layer. So as a result, a shear stress will be created. Okay, that is the thing. Suppose I can better you can, I can explain. Suppose this is the reference line OAA dash. So suppose this is the fluid position of this one earlier position, and suppose we are applying a shear force, and this position is continuously changing from this OAA dash to this OBB dash, and this continuously changing. But in case of solid it will not like that. In case of solid, if you apply a external force and you remove that external force, what will happen? It will regain its original shape and size, and it is not a time dependent phenomena. But the deformation in case of liquid, it is a time dependent phenomena. Okay, it is a time dependent phenomena. Just wait for a second. So it is a time dependent phenomena. Let me check. Yes. So it is a time dependent phenomena. The shear strength is keep on changing with respect to time. Okay, that shear strength is keep on changing with respect to time, and the flow is continuously in nature. That is called fluid. Okay. So now suppose this is the earlier position 1, this is second, and this is third, and this is 4, and the angular strain, or this is called angular strain, this is phi 3, is going to be more as compared with phi 2, and is going to be more as compared to this phi 1. Okay, so the angular deformation or the angular shear strain is greater, it is increases with respect to time. Okay, and that magnitude of the shear strain, angular shear strain, is directly proportional to the applied shear stress. Tau is directly proportional to rate of shear strain. Okay, and the rate of shear strain is called as flow, because if the angular deformation is existing, means the fluid is flowing, fluid is in dynamic condition. If the angular deformation will be 0, is the fluid is flowing? No, the fluid is not flowing. Okay, and some basic units, the density unit is mass, this is called kg per meter cube, and the force unit will be, this is Newton, pressure unit will be megapascal, this is Pascal, Newton per meter square, and work done unit will be, this is force into displacement, and this is called joule. Okay, power unit is called watt, that is called joule per. Basic units are there. So today we are going to talk about the properties of the fluid. Properties means what? The characteristics of the fluid which are not going to change when the fluid is coming into the motion. That is called fluid properties. Fluid properties will remain constant. Okay, so the first property of the fluid is called as density. So density means what? Density होता है आपका in the ratio between the mass of the fluid or the quantity of the matter per unit volume. Okay, in particular volume of the fluid, how much matter present, that is called density. Okay, so density is called mass per volume of the fluid. What is the unit? Unit is called kg per meter cube. So dimensional formula is, if you find out, this is m1 L minus 3. That's very easy. And density of the air is very less. So air is the fluid, density of the air, that is called 1.24 kg per meter cube, and the density of the water, that is 1000 kg per meter cube, or this is 1 gram per cc. So with increasing temperature, the force, intermolecular force of attraction in between the molecule decreases. As the intermolecular force of attraction in between molecule decreases, as a consequence the density will be decreases in case of liquid. Okay, but in case of gases, if you increase the temperature, the viscosity or intermolecular force will increase. Okay, intermolecular force will be increased, means the momentum exchange or a collision in between the molecule will increase. As a result, what viscosity is going to increase. That is separate thing. But with increasing pressure, the density is not going to change in case of the liquid. But as far as the gases is concerned, with increasing pressure, the gases density will increases. Okay, the gases density will increases, as vice versa. Specific weight, that is mass density, this is called specific weight, or this is called weight density. Weight density means the weight of the matter or weight of the fluid per unit volume. Okay, this is called weight of the fluid per unit volume. What is weight? This is mass into g per volume. Mass per volume, this is called density. So this is rho into g, and is also represented by, this is gamma. Okay, this specific weight is also represented by, this is gamma. So this unit is Newton per meter cube. You find out dimensional formula, it is very easy. So specific weight of the water is how much? This is rho into g. So this is 9.81 kilonewton per meter cube. third property of the fluid is called specific volume. So specific volume, it is the ratio of the or reciprocal of the mass density. Okay, reciprocal of the mass density. What is the requirement of the specific volume? Because some of the fluids like gases, like air, has very low density. So in order to make it to high value, we are actually taking the reciprocal of that one, 1 by 1.24. How much it is coming out? Generally it is coming out to be 0.78. okay, 0.78. so specific volume is the what? It is defined as the ratio of the volume of the fluid occupied per unit mass. Okay, and this is specific volume is, this is 1 by rho, and this is unit meter cube per kg, and reciprocal of the mass density, and it's generally commonly used for gases, and the specific volume of the air, this is 0.78 meter cube per kg. Fourth property is called as specific gravity. Specific gravity is a non-dimensional number, and it is used to identify which one is heavier fluid, which one is lighter fluid. Suppose you take example of oil and water. Oil specific gravity around 0.8 and water specific gravity 1. So that's why oil always floats on the water. Okay, so specific gravity is the ratio of the weight density or density of the fluid with respect to some standard fluid, standard density or the weight density or density of the standard fluid. So specific gravity, weight density of the fluid, weight density of the fluid divided by weight density of the standard fluid. Standard fluid means in case of liquid, the standard fluid is taken as water at 4 degrees Celsius, and in case of gases, the standard fluid taken as air. Why at 4 degrees Celsius? Because after 4 degrees Celsius, the behavior will be changed, the anomalous behavior will be will appear in case of water. So at 4 degrees Celsius, we are actually taking as the water standard fluid. So density of the water is how much? 1000 kg per meter cube. Weight density is 9.81 kilonewton per meter cube. So if you want to find out the weight density of the liquid, multiply the specific gravity with weight density of the water. If you want to find out the density of the liquid, multiply the specific gravity of the liquid with density of the water. So this is a small example. You can try at your home. This is also a small example. Try it at home. Now fourth property of the fluid is called compressibility and bulk modulus. So bulk modulus, it is actually what is the increase in strain with increase in pressure. That is actually bulk modulus. Suppose we take example of cylinder. This is a cylinder. Okay, we are applying a P amount of pressure into a piston. So the initial position of the piston will be P1. Suppose we are taking a fluid which is it is compressible nature. So now we increase the pressure by del P amount. Now what will happen? Now the position is going to change from 1 to 2. The fluid is compressed. How much the change in volume? This change in volume will be dV. This change in volume is observed due to change in pressure, del P. So this bulk modulus is nothing but this is what is the volumetric strain per change in pressure. Volumetric strain means what? This is dV by this is V. So this is actually bulk modulus. Okay, so reciprocal of the bulk modulus is called as compressibility. Okay, so ideally the water or liquid is considered as incompressible nature. So as incompressible nature, the dV part is going to be 0 for in case of liquid. So ideally in case of water, the bulk modulus will be infinite for water. Okay, ideally in case of liquid. So compressibility is what? This is the reciprocal of the bulk modulus. So compressibility represented by beta, and this is 1 by K. So bulk modulus is going to define by this is the increase, how much change in volumetric strain per increase in pressure, del P by dB by B, and this is the basic formula you have to find out. Why the negative sign is there? Because the B2 is going to be small as compared to B1. In order to make into positive, we are putting a negative sign. Okay, so for perfect liquid, I told you this is incompressible nature, means beta will going to be 0 because K is going to be infinite. K is going to be infinite, so beta is going to be 0. So this is K is dP by dV by D, and this beta, if you find out from this one, reciprocal of the bulk modulus, so this is compressibility. and since density will be equal to mass by volume and mass will be equal to density and volume, a mass of a matter is constant, mass will not change. Okay, so if you differentiate with respect to mass, so this is the relations we are going to find out. So minus dB by d will be equal to d rho by rho, d rho by rho. So the bulk modulus also can be defined, this is positive, so this is bulk modulus will be equal to, this is dp by this is d rho by rho, this is also bulk modulus. Okay, so so what is the physical significance of the bulk modulus? If the bulk modulus is very high, the fluid is very low compressible. If the bulk modulus is very less, the fluid will be more compressible. So compressibility and bulk modulus in case of isothermal process. Okay, isothermal process is what P is equal to rho RT. Okay, P is equal to MRT, or M by B will be equal to rho RT. If you, the pressure density is a function of pressure, so if you take the derivative of pressure with respect to density, we are getting this one. Okay, so the bulk modulus will be equal to rho into dP by d rho, we know this one. So in case of dP by rho, put this value and we are getting this equation 2. So if you equate this equation 1 and equation 2, so this K is coming out to be P. Okay, K is coming out to be, means for isothermal process or isothermal compression, the bulk modulus is going out to be pressure only. Okay, it is going out to magnitude of the pressure. What is the compressibility? Is reciprocal of the pressure. Okay, so now bulk modulus in the case of adiabatic compression. So adiabatic compression means this is a process in which there is no transfer or no exchange of the heat from the surrounding to the system or from system to the surrounding. So this PB to the power gamma will be called constant, and this gamma is called as adiabatic constant, that is coming out to be 1.4. So now if you take the derivative, finally that thing is coming out to be this one, dP by dB, very easy. And the bulk modulus is coming out to minus B into dP by dB. So dP by dB you put right over here, so we are going to get this one. So this bulk modulus is coming out to be gamma into P. So gamma is how? Adiabatic constant, gas constant, that is 1.4. Okay, that is the in case of adiabatic compression. This assignment for you, take this one. So now the fifth property of the fluid, very important, that is called viscosity. Viscosity, it is means it is a property of the fluid which offer the resistance to the flow, which offer resistance to the flow. So the fluid always flow in layer manner. Okay, the fluid is flow always in, suppose this is the bed part. Okay, so this bed part, fluids always flow in layer manner. Okay, fluid always flow in layer manner. So one layer velocity is greater than another layer velocity. Okay, suppose this top layer, this is top layer and this bottom layer. So this top layer is try to drag this bottom layer in this flowing direction, but as this bottom layer has less velocity, it is try to retard the motion of the top layer. So as a consequence, what will happen? A shear force will be developed in between these two layers. That shear force or shear stress is going to be generated due to the viscosity effect, and the fluid is a dynamic condition. This is the two thing. So viscosity is the fluid property whose effect will be understood when the fluid is coming under the dynamic condition only. Okay, so in a flow of fluid, when the fluid element move with different velocity, each element will feel some resistance to fluid friction in the element. Okay, so when the fluid will be coming under relative velocity motion, then there will be some resistance is we are actually feeling, or resistance is generating in case of the in between these layers of the fluid. And the relationship between the shear stress and this velocity gradient is first understood by this Sir Isaac Newton. Okay, so let us observe the flow. Suppose this flow is one, so this is water. Okay, and that we are applying a shear force by putting a plate on the top surface of the fluid, and suppose this is my 2 point. So suppose this is point 1 and this is this point is at a point at time t equal to 0. But what will happen when we apply shear stress? Now this point is moving to this final point, this point, within time period t1. What is the change in time? This is t. So within this time, the fluid is particle already changes its position. Suppose this fluid particle has been changed its position from this point to this point. Okay. And what will happen? This one fluid particle, it is tried to move this second particle along its direction. but the second particle, as its velocity is very less, what is it's try to drag the top fluid particle in opposite position, opposite direction. So as a consequence, a shear stress will be, shear force will be generated in the case of this fluid motion. Okay. Now you take the example of water and mercury. So in case of mercury, so as the mercury has a very high viscosity fluid, okay, intermolecular force of attraction is very high in case of mercury, so the angular deformation is coming out to very less in case of mercury as compared to the water. So angular deformation of the water is more as compared to the mercury. Why? Viscosity is more is the viscosity, less is the angular deformation, less is the viscosity, more is the angular deformation, provided the shear stress will be constant in both the case. So now Sir Isaac Newton has told this angular deformation d theta, it is directly proportional to the tau. Why we are writing this dt? Because this d theta is keep on changing with respect to this time. So this tau is directly proportional to the d theta by dt. So if you remove the proportionality constant, so tau will be equal to mu into this d theta by dt. What is this mu? Mu is equal to tau by d theta by dt. Okay, and the d theta by dt is called as rate of shear strain. Okay, and rate of shear strain. So now you take a case, this one, suppose this fluid particle has a velocity higher than compared to this. So this is suppose u plus tu, and this fluid particle has a velocity u. So because of this higher velocity of this top fluid particle, it has gone to some more distance. It has gone to some distance. This distance is how much? This is equal to du into dt. Increase in velocity is du into the time taken by this fluid particle from this point to this point is dt. So distance traveled by this one is du into dt. So this is the distance traveled by this fluid particle from this point to this point. Okay, so this is du into dt, and this is the angular deformation d theta, and the gap in between this fluid particle, suppose this one is dy. So what is tan d theta? Tan d theta, then tan d theta will be equal to du dt by dy. So as the tan d theta is very small, so we can take tan d theta will be equal to simple d theta. So d theta will be equal to du dt by dy. So d theta by dt will be equal to du by dy. So physically saying d theta by dt is not possible because the angular deformation is very small. It is not practically possible to measure d theta by dt. So another parameter we have to find out in place of d theta by dt. So that is called velocity gradient, that is du by dy. So I can write down this one. So tau will be equal to mu into this is du by this is dy. So this is called as Newton's law of viscosity. Okay, this theory is given by Newton, Sir Isaac Newton. So this is called Newton's law of viscosity. Okay, already I told you this thing. So tau will be equal to mu into du by dy, or this is tau equal to mu into d theta by dt. Most of the problem you will see d theta by dt is not given mentioned, the du by dy it is mentioned in most of the cases. Okay, so if you find out the shear stress, so if you find shear force, that is shear stress into area, so mu into a into y by u, this is the shear force. So what is the unit of the viscosity? Unit of the viscosity is shear stress into Newton per meter square, and velocity is meter per second per meter. So it is coming out to Newton second per meter square, and Newton per meter square is called as Pascal. So dynamic viscosity unit is called as Pascal into second. Okay. So now this is viscosity unit is Pascal second, and if you convert Newton is how much? Newton will be called, this is kg meter per, this is second square. Okay, so this is kg meter per second square, kg meter per second square. So this is kg, if you see 1000 kg, if you put this one, this is coming dynamic viscosity unit, also you can expect this is kg by this is meter into this is second. Okay, so kg 1000 kg, and this is how much? This is second, and this is 100 centimeter. So basically I am trying to say you can convert this Pascal second into poise. Poise is the CGS unit. Okay, CGS unit of this dynamic viscosity. So 1 Pascal second will be equal to, this is 10 poise. In most of the numerical, the dynamic viscosity is given in the form of poise. So you can convert this poise into Pascal second. sixth property is called kinematic viscosity. So kinematic viscosity is the density, dynamic viscosity of the fluid by density of the fluid. Okay, so dynamic viscosity unit is coming out to be, this is meter square per second. How it is coming? So dynamic viscosity, this is kg by this is meter into this is second, and density is how much? This is kg per this is meter cube. So if you solve, this is coming out to meter square per second, and CGS is centimeter square per second. This CGS unit is centimeter square per second, and this is called as strokes. Okay, this is called as strokes. So 1 meter square 1 meter square per second is called as 10 to the power 4 strokes. Okay, this is the problem you solve. Okay, so variation of viscosity with temperature. So first of all, we take the case of liquid. In liquid, there is intermolecular force of attraction is very high as compared to gases. So as the temperature increases, the intermolecular force of attraction or the cohesive force in between the liquid is decreases. So what will happen? The viscosity will going to be decreased in case of liquid if the temperature we are increasing. But in the case of gases, if you increase the temperature, the molecular momentum exchange will increases. As the molecular momentum exchange increases, they will collide with each other very fastly. As they will collide with each other very fastly, the resistance to flow is increases. So what actually trying to say, in case of liquid, the viscosity is going to decrease with increasing temperature. In case of gas, the viscosity is going to increase in case of increasing temperature. Okay, so viscosity of the water at 20 degrees Celsius, that is generally taken as 10 to the minus 3 Pascal second, and viscosity of the water, it is generally 50 times higher than the dynamic viscosity of the air. But kinematic viscosity of the air, it is 15 times more than the kinematic viscosity of the water. So this is the type of the fluids. So the fluid which obey this shear strength is directly proportional to du by dy, or this is d theta by dt. Okay, that fluid is called as Newtonian fluid. And this Newtonian fluid, the slope means what? The viscosity will remain constant, it will not change. Okay, but if the variation between the relationship between shear strength and the velocity gradient is not linear, in the non-linear kind of thing, that is called non-Newtonian fluid. And ideal plastic fluid means there is some initial shear stress we have to apply to move the fluid, that is called ideal plastic. Like toothpaste is an example of ideal plastic fluid. And the x-axis is called as ideal fluid because their shear stress will be 0. Shear stress will be 0 means that is called ideal fluid, because viscosity is 0 in case of ideal fluid. And the y-axis is called as ideal solid because the shear strain or the angular deformation is 0. As much as you shear stress apply, it will not going to deform. That is the ideal solid. Okay, so you just read this one, it is very important. So just remember the examples of these types of the fluid. Now surface tension and capillarity. Surface tension, it is the property of the fluid, okay, by virtue of which the surface of a liquid, it is just behave like a stretched membrane. Take the example of this A, B, C fluid particle. So if see this A particle, it is actually surrounded by number of molecules, water molecules, and these water molecules are attracting with each other. So the net force acting on this water molecule A is going to be 0. Okay. Similarly, you take the point number B. Similarly, all the molecules of the water is attracting with each other because cohesive force is there, same molecular, same nature of forces in same molecules. So here also the net force acting on this molecule is going out to be 0. But you take the example of C, the fluid particle which is present on the interface. This is called as interface. Okay, it is called as interface because it is a surface which is separating two surfaces. There is gases and this one is liquid. Okay, this is called interface. So you take a fluid element in this interface, and the force of attraction in the surface, it is cancelling each other, but you find the resultant force in downward direction, that is coming out to be in downward direction. When whatever the molecules are present in the interface, they are coming and they are actually having a downward resultant pull towards the downward direction. So what this means, a tensile force or downward pull is going to be feel or going to be occur in the free surface. Okay, when the free surface is under a tensile force, okay, a stretched membrane kind of thing. So the surface tension can be defined, this is the force per unit length of the fluid, force per unit length. Capillarity is basically, this is basically, remember, the surface tension, it is due to only the cohesive force. Okay, surface tension is only due to the cohesive force. Higher is the surface tension, higher is the cohesive force, and if the higher is the cohesive force, what will happen? Then the spreading characteristic will be less. So you take the example of mercury. You take a drop of mercury and pour that mercury into this surface. It will not spread. It will take a spherical shape. It will contract its area and it will not wet the surface. So more is the surface tension. So more is the surface tension, more is the cohesive force, less is the wetting characteristic, less is the spreading characteristic, and more is the angle of contact, and vice versa. Okay. So capillary is a phenomena by virtue of which if you insert a very small narrow diameter of tube inside a container, what will happen? The water is going to be rise. So if the diameter is more than 1 centimeter, then capillary phenomena is not going to be observed. So see this example, here is the diameter of the tube is more than 1 centimeter. So here is, we are not actually see the capillary rise in naked eye. Okay, so capillary rise is a phenomena, it is can be observed only when the capillary tube diameter is less than 1 centimeter or 10 millimeter. Okay, so in case of water, what will happen? The adhesive force in between this water molecule and this glass, in glass material, it is very high. It is very high. Okay, it is very high. So as the adhesive force is greater than cohesive force, the water is rising in case of the water, and the meniscus will be here as a concave. Okay, but in case of mercury, the cohesive force is greater than adhesive force. Rather the liquid will be rise, it will fall to certain distance, and the meniscus will be a convex meniscus. Okay, so that is the thing. The capillary rise is due to the adhesive force is more as compared to the cohesive force. Capillary happens when the cohesive force is stronger than the adhesive force. What is adhesive force? The force in between different nature of the molecules. Okay, adhesive force means water, glass, milk, water, like this one, air, water. So now you take example of droplet. First one, liquid droplet. Okay, so liquid droplet, you take a knife and you cut this liquid droplet at this XX point and you analyze this one. So the surface tension is going to be formed or going to be created at the perimeter part. Okay, along the perimeter part the surface tension is acting, and the change in pressure is, change in pressure means what? The pressure inside minus the pressure outside the atmospheric pressure. So if the bubble will be in equilibrium condition, the surface tension force will be equal to pressure force. Surface tension force is how much? Sigma into pi d, and the pressure force is how much? This is P into pi by 4 into d square. So what is the increase in pressure? That is coming out to be 4 sigma by d in case of liquid droplet. So in case of bubble, if you take the example, the outside is air, inside is air. So here will be two interface, air water inside interface, air water outside interface. If the number of interface will be high, more, the surface tension will be also increases, because surface tension acting on the interface only. So surface tension will be, this is 2 times sigma into this is pi d, and thickness of this interface is very small, it can be neglected. So what is the force? The change in force, pressure force, that is P by 4 into pi by 4 d square. So for equilibrium, the surface tension is going to be equal to pressure force. So this is 2 sigma into pi d into pi by P into pi by 4 d square. So this P is coming out to be 8 sigma by d. Pressure inside this liquid jet. Same, you take a liquid jet of cylindrical shape and take a knife and cut this one along this length direction, and this is the surface tension is going to be observed along this length. This is the length parameter. Okay. So pressure inside this liquid jet, why it is not acting in this part? Because the interface is not this one, because the fluid is continuously flowing along this direction, so surface tension is not going to be observed in along this direction. Okay, so as there is interface of the water and air is there, so surface tension is going to be created at this point. So what is the surface tension for this sigma into, this is one sigma into L, this is another sigma into L. So this is sigma into 2L. What is the pressure force? The pressure force is going to be act like this. This is the area on which the pressure is acting. This is P into L into D. So for equilibrium, the surface tension will be equal to pressure force. So P into L into D into sigma into 2L. So the increase in pressure in case, excess pressure in case of liquid jet is coming out to be 2 sigma by D. So in case of bubble, the excess pressure is 8 sigma by D. In case of droplet, the excess pressure is 4 sigma by D. In case of liquid, the excess pressure is 2 sigma by D. What is the ratio? This is 4:2:1. What is the wetting and non-wetting fluid? Wetting and non-wetting fluid means, suppose you take example of mercury. So this is the example of mercury and this is the example of water. So if you take the example of mercury, so if you drop a mercury on a surface, the cohesive force in case of mercury is very high. The cohesive force is very strong in case of the, as compared to this adhesive force in case of mercury. So what will happen when you drop a mercury into the surface? Immediately it will take a shape of spherical shape. Take a shape of sphere. It will contract this area. Okay. So as the cohesive force is going to be more than adhesive force, so what will happen? Surface tension of the mercury is very high, and it will not spread on the surface. It will not wet the surface. It will not spread the surface. So if you take this contact point and you draw the tangent, this theta is greater than 90 degree. Okay. But in case of water, if you pour a drop of water onto the surface, so what will happen? The water immediately it will spread. The water will immediately spread on the surface. It will wet the surface. Why? Because adhesive force is greater than the cohesive force in case of the water. Okay. So adhesive force is going to be greater in case of water. If you draw a point on a tangent on this contact point, this theta is less than 90 degree in case of the water. So if the angle of contact is theta, if theta is less than 90 degree, then the fluid is called wetting fluid. And if the cohesive force is less than adhesive force, then fluid is called wetting fluid. Because adhesive force is more, cohesive force is less, then the fluid is called wetting fluid, like water. And if theta is greater than 90 degree, the fluid is called non-wetting fluid. If cohesive force is more than adhesive force, then that is also called non-wetting. This is called mercury. Okay. That's why mercury is considered as a manometric fluid, because it will not stick to the manometer. Okay, it does not stick to the manometer. That's why we can observe clearly the increase in height or difference in height in case of mercury. So that's why mercury is considered as a manometric fluid, because of the what? First is this is high surface tension. Second one is called less wetting characteristic, and third one is called low vapor pressure. Okay, that is the three characteristic of the mercury. And fourth is high density, very high density. So expression of the capillary rise. So suppose this is the surface tension sigma. So this is sigma is acting, and this sigma is cos theta. Okay, sigma is cos theta is, take the component, and horizontal component sigma is sin theta, that will cancel each other. So this sigma into cos theta into this diameter is, this one is d, small d. So this diameter is small d. And this surface tension force at equilibrium condition, what will happen? The upward force will be equal to the downward force. The weight of the water is acting downward. So this is surface tension into perimeter into cos theta into the weight of the fluid. This sigma into cross sectional area into height into g. So perimeter is pi d. This is cos theta. So it is coming out to be 4 sigma cos theta by rho g t. What is rho g? That is called specific weight of the fluid. This is called capillary rise. And for water class, the angle of contact is taken as 0 degree, and for mercury the angle of contact is taken as 130 degree. 130 degree. Okay. So capillary flow, capillary flow, what will happen? The same sigma, you take the component of this one, this is sigma cos theta, and this diameter you take, this one is d. Okay, sigma cos theta into perimeter, and this is hydrostatic pressure force acting. What is the hydrostatic pressure? This is rho gh into the cross sectional area. So sigma pi d cos theta into this rho gh into pi by 4 d square. So h is coming out to be this one. So in case of mercury, there is a depression or there is a capillary fall, that is going to be 4 sigma cos theta by rho gd, and in case of water there is a capillary rise. Why? Because this force is more than cohesive force, and that is also same expression is coming in both the case. Okay, so capillary rise in case of parallel plate. Suppose you take a parallel plate and the thickness is very small. Okay, so what will happen? This is the surface tension at the interface. Okay, the surface tension will be interface at this one, so this meniscus and this plate, and you take the component in this one. What is the contact? The contact will be B. Okay, sigma cos theta into B into B. This is 2B. Okay, will be equal to weight. Weight will be how much? This sigma into A into H into G. This is the weight of the fluid. This is the weight of the fluid is acting downward, and sigma into 2B cos theta is the surface tension force. So what is the area? Area will be how much? This is B into T into H into G. So if you equate this one, this is the height in case of parallel plate, 2 sigma cos theta by rho g into T. So vapor pressure and cavitation means what? Vapor pressure is the property of the fluid and cavitation is the effect of the vapor pressure. So if you take a container, if you increase the temperature of the container, what is going to happen? The liquid from this surface is going to be vaporized states, and this, when the vapor will accumulate this top surface, free is the empty part, and it will come in saturated part, and it will exert a pressure onto the surface. This pressure are actually exerted by the vapor of this liquid. That pressure which is exerted by the vapor onto the surface, that pressure is called as vapor pressure. Means what? When the liquid start boiling, when the liquid start vaporizing, the molecules escape from the free surface and get accumulated in the space between the liquid surface and the top vessel. This accumulated vapor exert a pressure on the liquid surface, which is known as vapor pressure. Okay, so that is the thing. So what is happen? Vapor pressure, when the pressure in a pipe flow is fall below the vapor pressure, the liquid start boiling. Okay, so at low pressure region, the bubble will formation. So during the motion of the fluid, this bubble will flow along the direction of the flow, and when it will reach this high pressure region, they will burst. Like this, they will burst. So during the burst, what will happen? It will create a very high pressure. Okay, due to what will happen? This pipe material is going to be eroded. The cavity will be formed. This is called cavitation. So cavitation is the effect of the vapor pressure. So cavitation is always to be protected. It should not be allowed. It will destroy this this pipe system. So this thing is observed basically in case of the pump, turbine, and it is basically observed in case of siphon. So suppose this is a pipe, and this is a pipe in this case. So at this point the pressure is going to be fall below the vapor pressure. There is a possibility. So if the pressure is falls below the vapor pressure, the liquid start boiling at that particular point, and at the subconsequence the liquid that bubbles will be formed, and it leads to the cavitation. So cavitation always to be prevented. So thank you for today. So this is the chapter 1, end of the chapter 1. In next class I am going to start the pressure measurement and what do you mean by Pascal's law, hydrostatic law. Thank you.